So let's define a few new terms. First of all, I want to start with a random variable. So we talked about how an event is often represented by a capital letter from the beginning of the alphabet, say A, B, C, etc. For a random variable, we likewise tend to use capital letters, but actually from the end of the alphabet, X, Y, Z, and so on. And a random variable is a function that assigns a real number to each element of the sample space. So let me pause for a moment. So that's saying that the domain of a random variable is the sample space, and it's going to assign to each thing in that sample space some real number. Once we define a random variable, we then can talk about its mass density function. And this is entirely related to probability. So for random variable x, the mass density function is the function defined by little p of k. And that is supposed to represent the probability that random variable x is equal to the value k. So notice that the mass density function then has as its domain the range of x. And then the output of the mass density function has to be some number that's between 0 and 1 inclusively. So to make sure this is clear, let's look at a specific example. If I were to flip a fair coin twice, let's let x be the number of heads. So first of all, notice that x is a random variable. You don't have to do this every time you encounter a random variable, but to be clear, we've talked about this situation where the sample space here could be represented as using the letters H and T for heads and tails respectively. We could list out the 4 possible outcomes, and according to our definition, if x is a random variable, we should be able to see what number it maps each thing in the sample space to. So notice that x, if I were to evaluate this at HH, x should give you the number 2 because that says there were 2 heads. X of HT, counting the number of heads, is 1. X of TH is likewise 1. And x of TT is 0. So what I can tell right here is, again, the domain of the random variable is the sample space. And the range of x, the random variable, after listing what we saw above, I can see that the range is the values 0, 1, and 2. So these are the only real numbers that this random variable assigns to its input. Once I have that, then I can talk about the mass density function of x in this situation. So sometimes we might be asked to find the mass density function for a particular random variable. And I'll point out one thing that can feel strange about that is typically I think we're used to thinking of functions as functions that have as the domain an interval of real numbers, and we write those functions, say f of x is equal to x squared, or f of x is equal to e to the x. Here, the domain of the mass density function is the range of x. So the domain is just the numbers 0, 1, and 2. We call that a discrete domain. So the weird part about finding that is you're not going to necessarily write down a function expression for that. If you have a discrete domain, it suffices to identify where that function sends each of the things in its domain. So in this case, I need to be able to say what p of 0 is, what p of 1 is, and what p of 2 is. If I can do that for each of these, then I have found the mass density function, and my listing of these is my finding that. So p of 0, again, just to emphasize the definition, this means we need to say what the probability is that x is equal to 0. Likewise, p of 1 is asking for the probability that x is 1, and p of 2, the probability that x is 2. So that's just how I interpret this notation. To go back and find these probabilities, I'm going to notice that p of 0 has this one possibility. So the only way that our random variable took on the value 0 was if the coin landed tails twice. So I'm really interpreting this as saying, what's the probability of the event that just includes tails, tails? So this is shorthand notation. There are 4 possible outcomes. They're equally likely. This is 1 out of the 4. So P of 0 is 1/4. If I want to think about P of 1, notice that there are 2 ways that my random variable can evaluate to 1. So we have to consider that we get HT or TH, which is 2 out of my 4 possible outcomes. So the probability that x is 1 is equal to 2/4. And then finally, for 2, we come back and there's only one way that x evaluates to 2, and that's if we see heads, heads, which is 1 out of our 4 outcomes. Now, something that carries over from our principles of probability. So if you recall, we said if you sum the probability of all possible outcomes, you should get 1. That can be translated to this mass density notation such that if I sum over all possible values in the range of x, k, if I sum P of k, that must equal 1. And that's a nice thing to remember, because notice that I can verify here that in fact I do get 1. And again, if you don't get 1, then you probably are missing something. And so just kind of always going back and verifying that that's true is a good idea. And then the last thing I want to cover is to recognize that we can define lots of different random variables on the same sample space. So here x was the number of heads. If I now in the same scenario, let y equal twice the number of heads, my sample space is exactly the same as it was above. The difference now is that the range of my new random variable y is 0, 2, or 4, if you think about the possible number of heads and double it. And in this instance, if I needed to find the mass density, I would need to identify these 3 function values. P of 0, that occurs in the instance that we see no heads, which is 1/4 of the time. P of 2 can happen in one of 2 ways. We can either see heads, tails, or tails, heads. And then finally, P of 4 can happen if we see both heads and there's 1/4 chance. So notice that these probabilities are similarly broken up as 1/4, 2/4, 1/4, but they're associated to different values in this instance where I'm changing my random variable. And you can come up with other random variables. We'll see other examples where the range changes and the way the probabilities are broken up and distributed is very different.